What is a steel truss and its common types? A truss is an innovative structural frame constructed by connecting a series of straight, interconnected members in a triangular pattern. Trusses are favored for their ability to span long distances and support large loads. They also minimize deflection and are remarkably lightweight. Unlike many components in steel structures, trusses typically feature thin steel members with many voids between them. Rather than the materials, it's their geometry that makes trusses strong. Nowadays, the main downside to constructing with trusses is the cost of fabrication and on-site installation due to their large size. A well-known example of the use of trusses is the Sydney Harbour Bridge, where the arch of the bridge is a giant curved truss. Other common examples of trusses in structures include their use in roofs to create gables or pitched roofs and to support flat warehouse roofs. Trusses are particularly common in old factories and warehouses because labor was cheaper when these structures were built, which helped reduce the cost of fabrication. Now, let's examine how trusses work to carry loads. Truss members function purely under axial loading. When a truss is loaded, each member experiences either tension or compression, and together they form a stable structure to carry the load. It is important to note that loads should be placed directly onto a node on a truss. This prevents member sagging that could occur between nodes and ensures that truss members carry only axial loads. Now, let's examine what happens when a load, such as the weight of the floor and people and cars on top, is applied to a truss. In this situation, the members in the top row, also referred to as the top chord, will be in compression. This is similar to the top layer of a beam when it sags between two supports. Similarly, the members in the bottom row, also known as the bottom chord, will be in tension, just like the bottom layer of a sagging beam. While this is happening, the diagonal and vertical members between the chords, also known as struts, will be in either tension or compression. Whether a particular member experiences tension or compression will vary according to its position in the truss. For example, if you look at this vertical member and imagine the vertical load coming down into it, you will see that this member will be in compression. Furthermore, if you imagine this vertical member being pushed downwards, this action will stretch the two diagonal members, putting them into tension. Following on from this, if you imagine this diagonal member being pulled downwards, you will see that this action will compress this vertical member, putting it into compression. As you can see, the forces in the diagonal and vertical members alternate. One is in compression, while the other is in tension. Note that the forces in these members would be opposite if the diagonal members were installed in the opposite orientation. In that case, the diagonal members would be in compression and the vertical members would be in tension. You may ask, how do we choose the orientation of diagonal members? Often, we design diagonal members to work in tension, since they are longer and would be more stressed in compression. This consideration helps determine the orientation of the members. The next point to highlight is the importance of movement allowances in truss supports. If the supports are locked in place, external factors, such as thermal expansion and contraction, can subject truss members to additional or different loads, such as bending, which they are not designed to handle. To mitigate these external forces and ensure that all truss members experience only tension or compression forces, rotation or sliding allowances should be provided at the truss supports. The Sydney Harbour Bridge is a good example of a truss with built-in movement allowances. Visitors to the base of the bridge can see that the bottom chord of the truss is supported on a large pin, which allows it to rotate. And looking at here, you can find the sliding allowances, Another example of movement allowance is found in trusses used to support bridges that run between two buildings. This is necessary because if the buildings are made of concrete, movement might occur due to floor shrinkage as the concrete cures, or from lateral loads like wind. If the truss supporting the bridge is attached directly to these concrete floors, and either building moves, it will place additional loading on the truss. As a result, the bridge could be compressed between the two buildings or stretched apart by them. By allowing for movement, we avoid these extra loads that could otherwise damage the truss. Horizontal movement allowance at supports is essential in a bridge of this kind to avoid this effect. This is achieved by special bearing supports that allow the bridge to slide while bearing the truss weight and transferring it to other elements. The next question you may ask is, what types of members are used in trusses? Similar to braces, there is a wide variety of steel members used to create trusses, ranging from single equal angles to heavier members like universal beams or columns, especially where members experience significant loads. It's worth mentioning that a combination of steel sections can be used to design a truss member. This can range from a simple double equal angle or double PFC to more complex designs. In these cases, the connections along the member's length are critical to ensure they work together and transfer the loads effectively. As mentioned earlier, trusses are massive in size, so it's important to understand how they are installed on construction projects. In many cases, transport limitations and the nature of the installation process dictate aspects of the truss design. To address this, trusses are manufactured in segments and then installed piece by piece. For example, if you look at this truss, you will see that it has been manufactured in several segments. These segments are then joined together on the construction site to create the complete truss. In summary, trusses can span longer distances and support heavier loads than steel beams. They are also lightweight and conveniently allow services to be routed through them. While this is the case, it's important to consider the additional cost associated with their fabrication and installation when choosing between a truss and an alternative structural frames. See you in the next video. Teletraining produces the most practical content for the construction industry.